Thank you very much. Thanks very much to the organizers for inviting me. I hope the mic is going to work out. Before the talk, I already prepared one example. I wanted to do two, but well, I didn't have enough time in the end. So one is probably enough. Throughout the talk, P is going to be a poset, which is finite, graded, and bounded. So finite is probably clear. Graded means all chains below bottom and top have the same length, maximal chains. And bounded means it actually has a bottom and a top. Okay, so a very classical and well-studied class of posets. Here is one example, which I'm going to draw again here. So when we take the set partition lattice on 3 elements, this is such an example of a finite graded bounded poset. And before starting with my with the new stuff, I want to start with chapter 0 to tell you how this story started, which is the Chow polynomial of a poset. And last summer in June 24, I barely knew what Chow polynomials are. So everything you see here has been happening over the last 18 months. And I might have been as scared of them as some of you might be. I don't know. But I'm going to give you a combinatorial definition that is hopefully convincing enough that we can all study these objects because they're not complicated. It's namely the following. So the Chow polynomial of such a poset is a polynomial in one variable x, and we define it recursively by saying we sum over all elements in the poset, which is not the bottom element, and then we take the characteristic polynomial of the interval between bottom and my element in the variable x, and then take the Chow polynomial of the upper interval. So this is the Chow polynomial of the upper interval, and this is the characteristic polynomial of the poset. Actually, to make it correct, we divide by 1 minus x. And if you haven't seen this characteristic polynomial, I'm going to give a definition in the next chapter. But just so that you see, this is an extremely combinatorial definition of an object. And this definition was given by Ferroni, Matern, and Vecchi last year. And they basically did calculations in the incidence algebra to come up with this combinatorial description. And I've been present in the talk of Lewis, and I didn't know what the objects are. And as soon as I saw this very combinatorial definition, I thought this is something I want to study and I want to look at. So maybe some more words about it. So if the poset P happens to be the lattice of flats of a matroid, so if P is the lattice of flats of a matroid, if you don't know what that is, it doesn't really matter because we're not going to talk about them in much detail later on. But if you know it, this is exactly the class of geometric lattices. Then this object is actually equal to the Hilbert series of the so-called Chow ring of the matroid. So the Chow ring of a matroid has been gotten quite some attention over the past years. It was introduced by Feichtner and Juswinski in 2004, and then so it's kind of a generalization of wonderful compactifications of hyperplane of complements of hyperplane arrangements, and it was used in the context of Adripazita and Katz's proof of the log concavity of the characteristic polynomial. In particular, this Chow ring has a Kähler package, so it satisfies Poincare duality and Hart-Lefschetz. And these are two properties we're going to see later on appearing. Okay, so basically all I'm saying here is there is some important geometric construction in the back that people have been used and people have been studying from algebraic geometric perspectives, but we don't need any of that at this point because we can only start with this very combinatorial definition. I didn't say that yet, but if you have any questions, feel free to ask. So is there something already unclear? Okay. Then I was told to, no, this is the wrong one. I was told to use these boards wisely. So we now want to define many polynomials or combinatorial data to posets. And if you have questions, we're going to see some examples later on. If you have questions, please interrupt. So the goal is we want to define the so-called AB index of a poset, which is this psi there, and the extended AB index, which is this x psi there. So the section is called extending the AB index. So for us to define the object, so the first object we attach to such a poset is the Möbius function. So it goes from the, well, in the way that we define it here, it goes from the poset to the integers. And we want, in the example here, so the idea is, for the Möbius function, we want that the bottom element of the poset gets the value 1. And then we want that the sum of the Möbius function values of all lower intervals is 0. So when you take any lower interval, which is not the bottom element only, I want it to sum to 0. This means I need to put some value here so that this interval, the sum becomes 0, so this must be a -1. Right? So that -1 plus 1 is 0. The same here, -1 and -1. And now we want that the whole sum in total is 0, so that means this element gets minus the sum of those, so this element gets value 2. Can you all agree with this calculation? Okay. So the Möbius function, maybe it's actually enough. I mean, I can also write it down. So maybe psi of the bottom element is equal to 1. And then we want that the sum Möbius function values of p not equal to the bottom element, that this sum is, no, that's not what I want. This is, we want q smaller equal to p of q is equal to 0 for all p not equal to 0. Then we define the Chow poly that we already saw up there. And this is just the generating function of the Möbius function values according to co-rank. So this is equal to the sum p in p, and then Möbius function value of p, and then x to the rank of p minus the rank of small p. Yeah? So in this example, I didn't write it down, but in this example, we would get an x squared here. We would get minus 3x, and we would get a 2. Yeah? So in this case, the characteristic polynomial would be, as I just said, x squared minus 3x plus 2. Yeah, you just take the generating function. And then the Poincaré polynomial, so this is the heuristic polynomial. And the Poincaré polynomial of x is the same thing, the same data, but read backwards and alternating, getting positive signs. So this is some p and p, Möbius function value of p, and now it is minus x to the rank of small p. Yeah, so this minus x turns the negative signs into positive signs, and the co-rank goes to rank. That reverses the coefficients. So this is then just x squared, this 2x squared plus 3x plus 1. Okay? And now the next, we are not done yet, so there are more polynomials to come. So that's the Poincaré polynomial. Yes?
Do you care the mu alternates inside, or does it matter?
Yes, I do care, but I ignored it for now. I mean, later on we want that this is positive, which is the same thing as saying the Möbius functions alternate in sign.
Is that automatic from the definitions?
Well, you can, no, it's not in general, it's not true. So when you take general graded posets, they might not alternate in sign. They might also be zero values. So for example, when you take the hexagon poset, like the weak order on S3, you're going to see zero values. And then it's also not alternating in sign. But in the many cases, in particular for lattice of flats of matroids, it is alternating in sign. Then the chain polynomial. The chain polynomial of the poset is the following. Let me write it. C of x. It is just your sum of all chains in the poset, whatever they are. So subsets of pairwise comparable elements, and then just x to the size of the chain. So if your poset happens to be when you do the chain polynomial, this is exactly the same as producing the f vector of its of its chain complex. Yeah. So when you take a poset and you produce the corresponding complex of chains, this records exactly the f vector of these chains. So that's the chain poly. Yes.
Are you looking back to strictly increasing or weakly increasing?
Strictly increasing. Everything we do here is strictly. I mean, then later on you might want to do also weakly increasing, but that's not happening in this talk. And now we come slowly to the objects in the definition, in the title of the talk, namely the AB index, psi. Of AB, and I mean I ignored the p's in the indices, but if I need the poset to be carried into the polynomial, I'm going to write it into the index wherever I need it. This is equal to the following object. So it's again the chains, and then it is the weight of the chain in A and B. I'm going to tell you in a second what that is. And this is a polynomial now in non-commuting variables A and B. So the others are just polynomials in one variable x, but now we have non-commuting variables A and B. And for the chains, for the AB index, for this definition of the weight, I want to do it at an example because that's much easier to do. Actually, we want the chains for this object to end in the top element. So let me just write this as C0 smaller ck smaller ck plus 1, and this is the top element. So can you all see this board well? So if this is your poset, the poset we looked at the beginning, we look at all chains that end in the top element. So it's only the top element, bottom and top, one of these three middle guys and the top, or bottom, one of these three middle guys and the top. Yeah, that's the possible chains. And now the weight is, I'm just recording which ranks happen to be in the chain and which ranks don't happen to be not in the chain. Yeah, and if a rank is not in the chain, I'm recording a factor a minus b. And if a rank is in the chain, then I'm recording a factor b. Okay? So the ranks 0 and 1 are both not in the chain. So I'm recording an a minus b times a minus b. But keep in mind, this is equal to a squared minus ab minus ba plus b squared. So it's non-commuting. Yeah? So the ranks are actually keep being recorded because they don't commute. So you know which ranks are there and which are not. So 0 and 1 means rank 0 is in there, so I record a b. Rank 1 is not in there, so I record an a minus b. Okay? So this is ba minus b squared. This is ab minus b squared. And this is, well, b squared. Okay, so here you see rank 0 is not present in the chain. Rank 1 is present, so not present and present. This is how you get the weight. And I ignore the 1. Of course, I could have appended a b on the right on every monomial, but it's not carrying any information. Okay? And now the AB index. Is just the sum of all those chains. So we are summing this object plus this plus 3 times this plus 3 times this, because this chain happens to exist 3 times for each of the 3 middle elements in the same here. And when you sum them all, you're getting exactly this polynomial, a squared plus 2ab. I mean, if you want to look at it, so you see the a squared here, then what about here's a minus ab, here's a 3 plus ab, so that's a 2 plus 2ab. Then we see a minus ba here. We see plus 3ba. Plus ba, so they both cancel. We see a b squared here. We see a minus b squared here. We see a minus 3b squared here. And we see a plus 3b squared here. So they also cancel. Okay? So this is how you get this polynomial. And in general, this is like a special class of such posets which are called R-labelable. So those that admit an R labeling. An R labeling is an edge labeling of the poset, so that every interval contains a unique increasing chain. So let me put one here. So this would be an R labeling. So for every interval, you just check there is a unique increasing chain. The only interval that actually is interesting in this case is the full interval, and you see there is one increasing chain. Yeah? For example, EL labelings, which you use to shell posets, to shell simplicial complexes. EL labelings are special cases of R labelings. And if the poset has an R labeling, then the AB index is always non-negative. But in general, it can have negative coefficients. Okay, so this is these are all classical polynomials on posets, and now the new one that we introduced last year is the extended AB index. And it is the same definition as before, but every chain is multiplied by the product of the Poincaré polynomials of the intervals. So sum of all chains C as above, and then we take the product I from 0 to k, and then the Poincaré polynomial of the interval ci plus 1 in a variable y, and then weight of c. So this is a polynomial in non-commuting variables a and b, and the coefficients are polynomials and y. So like as a gimmick, what you think of here, you have your complete poset, which maybe looks like this. Then you pick a chain, which is maybe this object, including the top element, so I'm also having this one. And then I'm taking the Poincare polynomials of these small intervals here and multiply them all together. Yeah, this is how you can think of this extended AB index. So for each such chain, you record the ranks and the weight, and record this product of the Poincare polynomials of these intervals. And of course, this is kind of looks like a very ad hoc definition. So my goal now is to convince you this is a reasonable definition, and I still have 40 minutes. So if you really want me to, I can also start attributing things to people, but I also think you can also look at the paper to see this. So this is definition with Galen and Josh from last year or 2 years ago. And so a first step to convince you maybe is the following. We want to see how the AB index is related to the Chow polynomial. I mean, the Chow polynomial is an object that I hope I don't need to convince you, because you might have heard of people doing important things on those. But you see this recursive definition of the Chow polynomial, when you make it explicit, you see that you're also taking products of these reduced Chow polys. Yeah, you take a bottom interval, and then you iterate the same step. So you take the next interval and the next interval. So you can make this definition up there explicit by just saying you sum over all chains in P, not containing the bottom element. And then you take the product of these reduced Chow polynomials. Yeah? And I mean, this is the definition that I knew before I attended Lewis's talk. And then I saw his definition, and I really saw this must be matching the same object. And the bottom one is like the much more fine. It's a much finer version of the Chow polynomial. So let's write that down. So so maybe let's start with some easier ones. When you plug in y is equal to 0, you're getting back the classical AB index. Why is this the case? Well, because the Poincare polynomial has constant term 1 always. Yeah, so if the Poincare polynomial has constant term 1, that means if you plug in y is equal to 0, they all turn into 1s, and this prefactor just completely disappears again. Then the second thing is yeah, I'm going to say it in a second. So it happens to be that there exist two such Chow polynomials, the usual Chow polynomial and the augmented Chow polynomial. They are closely related and mimic very similar behavior. The augmented one is easier to study, and also in our context is more natural to study. I didn't give you the definition, but it's almost the same definition. And it is not super hard to see that this augmented Chow polynomial is a direct evaluation of this extended AB index. So when you set, and you can actually do that yourself by hand if you wanted to. If you set into this function here y to minus x, a to 1 and b to x, you get back the definition up there. And this is basically because pi and chi are related by one is the other, but it is minus x inverse. Yeah? So, and this is exactly what you do in order to get from there to up there. And then this factor here is because you get from the Chow poly to the reduced Chow poly, which is just dividing by x, 1 minus x. And what is this object? This is the one that I haven't explained yet. So how do I get the actual definition up there? This is you take every AB monomial and delete the initial letter. I could again explain why I should do that, but this is not super hard. This is just going from chain starting anywhere to chain starting at the bottom element. So let's look at this example here. So we have already seen the AB index and computed it. Now we can do the same for this extended AB index. And so that means we weight every chain by its Poincaré polynomial, which I've written on the left. And here you see the full Poincaré polynomial that we actually computed here by hand, just in the variable y. And when you weight those chains by those coefficients, you're getting this polynomial in a and b, with coefficients being polynomials in y. Okay? And when we now delete the first letter from every AB monomial, this and this are merged into A. So the A squared becomes an A and the BA becomes an A. So those are merged to this object. And here the A is deleted, what do I want to do? Here the A is deleted and the B is deleted. This becomes the B. So those two are merged to this object. Okay? And now when you do this evaluation that I've written there, you can do it by hand or believe me, or you can also watch me making mistakes on the board, but I would prefer not to do that. When you make this evaluation from here, that's written there, you're going to get this polynomial. And if you make the evaluation on this object, you get this polynomial, which are Chow and augmented Chow in this case. Okay? Again, are there questions at the moment? Yes?
I'm sorry, you probably said this in words, but can you give the write-up? So for this reduced extended AB index, you're replacing pi with like some pi reduced or something? Or?
You mean for this object here?
Yeah,
no, this is how I delete the first letter from every AB monomial.
Delete the first letter.
So here is the example. This is the object itself. And when I delete the first letter from A squared, I get A. If I'm deleting the first letter from BA, I'm also getting A. So the coefficient of A is this, the coefficient here plus the coefficient here, which is this object. So this tilde doesn't have anything to do with this bar up there. These are two objects, but not directly related. And so in one of those projects with those co-authors, what we then do is, when we write down Chow and augmented Chow as evaluations of this AB index, that means we get for free a positive gamma expansion of these objects, which has been known only so far using these terms from the Keller package. So when you use the Keller package, people have known that these are gamma positive. So that means when you write them in gamma expansion, you get positive coefficients. But this gives you combinatorial descriptions of those. Yes? That's right.
Is that due to like March Bayer?
Yes. This is like in the first papers on those. It's maybe via Sturmfels, I think. More questions? Okay. So now I want to do. So this is like the first line of why you can hope this is something interesting. It's like a very refined version of, for example, the Chow polynomial. Let me add a few theorems. This one is with Galen and Josh. namely if the poset is the geometric lattice, is the lattice of flats of a matroid, then this polynomial has non-negative integer coefficients, which count certain chains in the poset. And this is the original motivation why we introduced these objects, because between this extended AB index and this Chow polynomial, there's another object in between, which I define in a minute, the coarse flag Hilbert-Poincaré series. And this was defined by Josh Maglione and Christopher Foll in the context of Igusa-Zeta functions from number theory. And they conjectured their functions to be non-negative. So we introduced these objects to prove their conjecture on the non-negativity of those Igusa-Zeta function evaluations. And a second theorem with my student Elena and Lorenzo Vecchi is the following. So here we see how to get from the extended AB index to the AB index back by like a trivial evaluation, because the constant terms of these Poincaré polynomials were all 1. But you can also go the other direction. So not only this guy knows this guy, but also the AB index already knows the extended AB index. So if you only give me the AB index, I can recover the extended AB index immediately. Namely as follows. The extended AB index is equal to a so-called omega evaluation of the AB index. And I tell you this story because this is connecting the AB index with the CD index on one hand, and also connecting the intersection poset of a realizable matroid with its phase poset. So what is this operation? And I'm going to be a little vague what it does. So this operation is, so this is a sum of AB monomials. So it's a sum of words in A's and B's. Okay? And omega takes such a word in A's and B's and first look at all instances of the consecutive ABs. So it takes first the ABs in such a word and replaces it by 1 plus y AB plus y 1 plus y BA. So it's really blowing it up drastically. Yeah? So now we've taken care of all the ABs in such a word. Now there are some A's and B's left in the remaining letters, and they are replaced as follows. A is replaced by A plus YB, and B is replaced by B plus YA. And one second. And yes, it's slightly too much to parse such a definition. So after the question, I'm gonna motivate why this is a reasonable definition. Yes?
So you first split the word into ABs and remaining A's and remaining B's, and then you separately do the.
Exactly.
Or if you do it consecutively.
No, you do everything at the same time. So you don't, the A's and B's that appeared here, you don't parse again through those.
Okay.
So you take this one monomial, you split it into ABs and A's and B's, and then you do all three at the same time. Okay? And this is a very weird operation a priori, but I mean, it's the right operation because by construction it actually produces the Poincaré polynomials of the intervals. So it must be some natural operation. But what happens if you plug in y is equal to 1? Then you get AB is replaced by 2AB plus 2BA, and A is replaced by A plus B, and B is also replaced by A plus B. And that's exactly the operation that goes from the CD index to the AB index, if you know what that is. Yeah? So when you write this as a polynomial in C and D, and then you replace C's by when you replace c's by 2ab plus 2ba and the d's by a plus b, you get exactly this evaluation for y is equal to 1. So it's a one parameter generalization of the operation that takes CD index and moves it to AB index. And if this is still not enough to convince you, I try to do the following. So when you have a realizable matroid, so say when you have a hyperplane arrangement, like our all favorite, most simple, non-trivial arrangement, then what is the intersection poset of this arrangement? Well, I'm taking all intersections of hyperplanes possible. So I can either intersect everything. This is actually the top element here. So we order by reverse inclusion, each of the three hyperplanes individually, or no intersection at all. Yeah? So this is the origin. These are the three hyperplanes, and this is the full space V. And when you, for this poset, when you write down the AB index, we've just done it, it's this guy, a squared plus 2ab. But this is a realizable matroid, so I mean it comes with a face poset, this hyperplane arrangement. It's now not intersections of hyperplanes, but faces. So a face is either the origin, either of those 6 rays below the origin. So here's the origin, here are the 6 rays below the origin. Each ray lies in 2 maximal cones. Each ray lies in 2 maximal cones in a cyclic order. So you get this crown poset. Can you all see how you get the crown poset? Let me do it once more. I'm taking all cones in this fan here. So the origin cone is here on top. The 6 rays of this fan are the 6 rays here. And the 6 two-dimensional cones are the 6 two-dimensional cones down here. And the containment is just cyclic containment, so that's a crown poset. But of course, there's a map from here to here that takes a cone and sends it to a linear span. So there's a natural map from here to here. And now you can convince yourself that when you want to write down the AB index of this face poset, so the AB index psi of the face poset of sigma in A and B is equal to the evaluation of the extended AB index of the face poset evaluated at 1. So this connection between face poset and intersection poset is exactly the original motivation to get between AB index and CD index. So for y is equal to 1, this operation is mimicking exactly this object. But on the other hand, this now allows you to define the AB index of a non-existing face poset for non-realizable matroids. So if you have a non-realizable matroid, it doesn't have a face poset, but you can still now study its AB index, because you can still study this object on the intersection poset and evaluate it at y is equal to 1. Okay, so this is the second property I wanted to show there. And now, before going to the last section, I want to finish this part with multiple open conjectures. Or questions. I mean, this is kind of a tautology, right? Athanasiades and Calamboya Evangelinu conjectured the face poset, the chain poset to be real rooted. This is Athanasiades and Calamboya Evangelinu in 23. Did I write it down or did I forget it? Of course, also the chain polynomial is also an evaluation of the extended AB index by construction. It's even an evaluation of the AB index itself. So this is real rooted. Then a major conjecture in matroid theory is that the Chow polynomial is real-rooted. This is Ferroni, Matern, I forgot, and Vecchi in 23. Can please someone check out who this S is again? Stevens, thank you, yes. They conjecture the Chow polynomial of a geometric lattice to be real-rooted. And also Lukas Kühne, who is here or was here, and Josh Maglione, they conjectured that also the so-called coarse flag Hilbert-Poincaré series is real-rooted. This is the coarse flag Hilbert-Poincaré series is between extended AB index and Chow, and I'm going to define it actually in a minute. But they also conjecture this to be real-rooted. So these are three different groups of people working on three different polynomials related to posets, and they all conjecture in the case of geometric lattices that these are real-rooted in all evaluations of this extended AB index. So please, can someone bring me an evaluation that's not real-rooted in the first place? I don't know of any, but there must exist some. I haven't actually tried finding some, but I really want to use this extended AB indexed machinery to prove real-rootedness of all of them at the same time, if possible. And maybe some partial progress. So for all of them, in the case of Cohn-Macaulay simplicial posets, which is, well, it's a class of such posets. These are known to be real-rooted. But simplicial posets are those where all lower intervals are Boolean, so that's an extremely strict restriction. So it's a very small class of posets. So the question here is, which evaluations of the extended AB index are real-rooted? And again, the motivation, this Chow polynomial is known to be gamma positive. I've at least mentioned a combinatorial proof of this property, but they're also known to be log concave. And this is related again to this Adebrezito-Hurkacz construction for the chain polynomial. As I just learned an hour ago, it might not actually be them who proved their log concavity, so I'm not making any claims who actually proved log concavity of those polynomials, but real rootedness is stronger than log concavity or gamma positivity. So if you or I or we find a proof of real rootedness in this case, it will in particular reprove those rather important statements. Okay, I'm now gonna switch gears for the last 15 minutes. So are there questions at the moment? Or more questions at the moment? Yes?
Comment, it's not log concave. I mean, it's not known to be log concave. It has been only pre-modality in gamma positivity is known for HF.
For this one?
Yeah.
Okay.
You're thinking of characteristic.
Let's see. Okay. Maybe, maybe not. Okay.
Could you say again why the Chow polynomial is gamma positive?
I didn't say why. I just said how. So we get this evaluation here. So we get the Chow polynomial as an evaluation of this extended AB index. And since this object can be written as this omega evaluation of this object, I can plug in this evaluation into omega, and then actually every AB monomial gives exactly one gamma summoned. So as soon as the AB index is positive, every AB monomial gives you a gamma summoned. It's going to give you an intrinsically positive gamma expansion. So as long as the AB index is positive, the Chow polynomial is gamma positive. And for geometric lattices, these are R-labeled posets, so their AB index is positive. Is that enough? Okay, more questions? Yes. So the lattice of flats of a matroid always exists. But the face poset does not always exist. It only exists for orientable matroids. Yes, thank you, for realizable matroids. Actually, you can also do it still for orientable matroids. That's fine still. So it's a slightly larger class. For orientable matroids, you still have such a face poset. And then you can just study the AB index of this face poset. Okay? And then it turns out that the AB index of this face poset is an evaluation of this extended AB index of the intersection poset. Since this object exists in more generality, you can now study this object in more generality even though these objects don't exist anymore. So it's just a tool to partially extend properties of orientable matroids to non-orientable matroids. More questions? Okay. Maybe I stick to one word for now. So the only object that I didn't, or the only polynomial that I didn't introduce so far is this coarse flag Hilbert-Poincaré series in between extended AB index and Chow. So let me give you this definition. It basically perfectly fits the pages on top. So we have CFHP. It's a polynomial in two variables, y and t. And you sum over all chains. But in this case, you want to start with 0. And end with 1 anyways. And then you take the Poincaré polynomial of this chain. I didn't give you the definition, but this is just this product up here. So can I also pull it? Yes. So I want to call this whole thing, I want to call pi of the chain in y. Pi of the chain in y, and then t divided by 1 minus t to the size of the chain. And then you immediately see, how is this related to this up there? Well, the Poincaré polynomial is the same, the coefficient is the same, but now the weight is turned into this object, yeah? Which is basically saying the b, so weight, remember, the weight was either b's or a minus b's, depending on whether or not you are in the rank is in the chain present or not. So if you're present in the chain, you are a b, and this is going to get the t's. So b is sent to t, and then a minus b must be sent to 1, and the remaining guys go here. So if you write this down properly, this is exactly equal to the extended AB index when you delete this first letter in y, 1, t, and then divided by 1 minus t to minus the rank of p. And then you see how this is in between extended AB index and Chow polynomial, because the Chow polynomial was the same evaluation, except that y was also set to, well, t was x and y was minus x. Yeah? You see that this is actually along the way between the two. And I want to set this guy from now on. This is now a polynomial that we're going to be looking at for the remaining 10 minutes. So it's between extended AB index and Chow. And the properties I want to focus on are the following. And I'm plugging in y to 1, I'm getting the following. I'm getting, for p is equal to, so this is again only for realizable matroids, for letters of, for intersection lattices of hyperplane arrangements. Then we get, this is the number of regions in the arrangement times the Eulerian polynomial in of rank n. Okay, so when you plug in y to 1, you're actually getting back a multiple of the Eulerian polynomial. The Eulerian polynomial was the general function of descents on permutations. So this is equal to the sum of all permutations sigma, and then t to the descents of sigma. Let's see if we can see that in an example. So the coarse flag Hilbert-Poincaré series in the example we are all the time looking at is this polynomial. Or the series is actually, when you divide the polynomial by this guy. So let's see that this works out. We start with this x psi that we already looked at. And we are setting a to 1. That's all we do, right? And if you set a to 1, this becomes the constant term in t. And this becomes this object times b, times t. Yeah? And when we now plug in y to 1, this is the evaluation we are doing here, y to 1, we are getting here 1 plus 3 plus 2 is 6 times 1 plus 6 times t is 6 times 1 plus t. Yeah? So when we do this evaluation, we get 6 times 1 plus t, which is 6 times the Eulerian polynomial in rank 2. Is that okay?
But is that a Eulerian polynomial of one less?
Yes. So yeah, the answer is yes. You want to see more about it. So what you look at here is the 6 is the size of S3, and this is using S2. Was that the question? And also, the second, when you evaluate at t is equal to 0, y and t is equal to 0, you're getting back the Poincaré polynomial in y. So the constant term in this evaluation in t, so that is actually this term, and that's actually the coefficient here is actually again the pi that we computed up there. Yeah? So all these objects are closely related. But now we have seen that, where did I give it? This object, we've proven that this object has non-negative integer coefficients. So we actually want to find a statistic that produces these numbers. So the question is, again for you to look at if you want to, the question is find, and I call it a companion statistic for descents. So find a companion statistic ST say from the regions times the symmetric group in n letters, from the regions of the hyperplane arrangement times sim n into the integers such that this polynomial n of y comma t is equal to the sum, and now R is the region and sigma is a permutation, and then it is y to the st of r comma sigma, and then t to the descents of sigma. Okay? So again, if you lost track of what's happening, we slightly shifted gears from motivating the extended AB index using the Chow polynomial mostly. We moved to describing something intermediate between Chow and this extended AB index in a purely combinatorial manner. And maybe I can keep going here. Is it clear what I'm trying to do there? Or not too much? So what I'm trying to do is, this is a polynomial in y and t with non-negative integer coefficients, and I know that I'm setting one of the constant term in y is the Eulerian polynomial. The constant term in t is the Poincare polynomial, and the evaluation of y is equal to 1 is a multiple of the Eulerian polynomial. So I want to match something with the Eulerian polynomial that gives the full object, which is this question here. So to make an intermediate statement, if the arrangement happens to be a reflection arrangement, so if A is equal to A of W for a finite Coxeter group W, then the regions are actually labeling the elements of the group. So this question becomes, find a statistic ST from a reflection group W of rank n times, what did I call the symmetry group in n letters to the integers, such that with n of W yt is equal to the sum W in W, sigma in sim n, and then y to the st of W comma sigma, t to the descent of sigma. And this is exactly what César asked. For the symmetry group in n plus 1 letters has rank n. This is why for the symmetry group you sum over pairs of permutations. One is one longer than the other. Yes? Okay. And together with my student Elena, we proved the following theorem. That if W is Sn plus 1, I'm trying to distinguish one to be a group and the other to be just permutations. So I call them slightly different so I can actually distinguish the two. So we defined a statistic, an in-order statistic. I'm not giving the definition, but the in-order statistic generalizes left to right minima in permutations. So the in-order statistic is generalization of left to right minima, and this statistic does give you, for the braid arrangement, gives you this evaluation. But in particular, when you solve this problem for general reflection groups, you in particular generalize left to right minima to general reflection groups. And this is another open problem that's open for 20 years. People have tried to find Coxeter definitions of left to right minima, and they all failed, or maxima, or right to left, it doesn't matter. So in particular, if you solve this problem for reflection groups, you automatically generalize left to right minima to other reflection groups. So it's another motivation to look at these types of problems. So to finish, I defined this big polynomial. I evaluated it to get the Chow polynomial, and then I looked at the situation of reflection arrangements, and I gave you some questions to look at in the case of intersection or lattices of flats of matroids. And here I'm giving you more questions and open problems for hyperplane arrangements and reflection arrangements. And please talk to me if you want to solve them. Thank you very much.